So today we will see how to solve recurrence problems. So what exactly is a recurrence problem? In this we try to represent a bigger problem in terms of similar smaller problems. So we'll see an example. So we will try to fill a binary sequence of size n. So I will have n positions which needs to be filled. Now I'll take one position and start filling. In this one position, either I can fill it with 0 or I can fill it with 1. So no matter how I fill it, I will still have n minus 1 positions remaining to be filled after I am done with 1. Here also, after I am done with filling, I will have n minus 1 positions to be filled. So let me take T of n has the number of sequences of the length n. How many sequences do you have? So you can tell number of sequences of length n is number of sequences of n minus 1 plus number of sequences of n minus 1. So it is 2 times n minus 1. Now if I want to take again n minus 1, so after I fill the next position, again I will have n minus 2 ways. Here again I will have n minus 2 and n minus 2 ways. So this recurrence relation keeps on continuing. When will you stop this loop? So to stop such a recurrence loop, you will need to know at least the answer to the smallest possible value. So what is the answer to the smallest possible value? If our size was 1, we only had one position, then we know that we can either fill it with 0 or 1. So that will become our base case. So the number of binary sequence of length 1 is 2. That is, we fill it with either 0 or 1. So this will become the base case. So I can tell T of 1 will be equal to 2. Hence I can write this particular problem in a recursive way like this, that is T of n is 2 times T of n minus 1 if n is greater than 1, and then when it becomes equal to 1, T of n is 2. So another problem we'll see. So now you can see a loop which is recursive, that is I have void test void test n, and this is calling n minus 1. So when I again run the n minus 1, it will call n minus 2 and so on. So the major work done in this particular code is printing. So I've done a tree here. So suppose I call my n has 3. Just imagine I'm telling n has 3. So I will pass test 3. What it does exactly? 3 is greater than 0. So it will print 3. So first work that is done by it is printing 3. Then another thing what it does is it calls test of n minus 1. So 3 minus 1 is 2. It calls test 2. This test 2 again will come. What it does, it prints 2 and calls test 1. So up to when it goes, you know that when n is equal to 0, it stops. So test 0, it doesn't call anything and it returns from the function. So how can I write a relation for this? So I'll tell f of n is f of n minus 1 plus, I'll tell this particular printing operation takes 1 unit of time. Maybe whatever time it is, 1 unit of time for printing, and it takes again same relation f of n minus 1 plus 1 whenever n is greater than or equal to 1. When it becomes 0, what happens? It returns. Again I will take, for returning 1 unit of time is taken. So when n becomes equal to 0, it only returns, but when n is greater than 0, it has to print plus again it has to find f of n minus 1. So this way I formulated a recursive relation for this particular code. So now we will see how you can solve such a recursive relation. We have 3 methods in which we can solve a recursive relation. The first one is called as the substitution method. The other one is the recurrence tree method, and other is the master method. So we will see substitution method in this video. So we'll take an example here. See here we have an example, T of n equal to 1 if n equal to 1, which is our base case, and it is n into T of n minus 1 if n is greater than 1. This is our recursive case. Now we will solve this by substituting this again and again. So how it is done? So I've taken t of n equal to n into t of n minus 1. Now we know that this t of n minus 1 again can be put here and we can get something. So what will be t of n minus 1? T of n equal to n into t of n minus 1, right? Now here our n itself is n minus 1. So t of n equal to n into t of n minus 1. So what happens when we solve this? We get equal to n minus 1 into t of n minus 2. This thing we will again substitute here. So what will happen? We get t of n is n into, this one is n minus 1 into t of n minus 2. Now again this t of n minus 2 can be solved in the same way. So again I will write t of n minus 2 is this n minus 2 into t of n minus 2 minus 1. So I will get n minus 2 into t of n minus 3. Again this I will substitute back. So I will get n into n minus 1 into n minus 2 into 3 of t of n minus 3. So these things keep on going. So I don't have to again solve like this. I know the sequence how it is going now. So I'll write next step obviously will be up to n minus 3. This t of n minus 3 will be split as n minus 3 into t of n minus 4. The next step, this t of n minus 4 will be written as n minus 4 into t of n minus 5, and this will keep on going. Now till where will you take this? Till when will this particular thing keep going? It is when till you reach the base case. So this is why we need a base case. So which is the base case in your problem? When t of n becomes 1. So t of 1 equal to 1. This is our base case here. So we will take, when will your t of this whatever you're doing become 1? See, it is n minus 5. So when I do n minus 1. So n and n will cancel and it becomes only 1. So I have to do t of n minus 1. So till n minus 1 I have to keep on repeating this procedure. So I will write t of n equal to n into n minus 1 into n minus 2 into so on. Here see, till the end how will you get t of, here we need n minus 1, then here also it will come up to n minus 1. See, here we have 5, it will come up to n minus 1. So I'll have t of n minus 1 into t of n minus 1. Now this particular thing is our t of 1, and this also will solve to 1. N minus n, this will cancel, minus into minus plus, it will become 1. So I'll write it again. It is n into n minus 1 into n minus 2 and so on. So we get 3 into 2 into 1. Again this will be the 1. So as you can see, this is nothing but our n factorial, right? So our t of n equal to n factorial into this one. So you can see here I can tell this is f of n equal to some g of n into some constant c. So now we can use our knowledge of asymptotic notations, and I will represent if your f of n equal to c into g of n, right? T of n is big O of n factorial, because this will never become bigger than n factorial. So this particular problem has the factorial time complexity. So remember we saw this problem of that recursive tree, the code which we did in the previous section. So now this t of n equal to t of n minus 1 plus 1, where we are printing, that is n greater than 0, and it is 1 if n equal to 0 for returning. So this problem also we will try to solve now in substitution method. So we know that t of n is t of n minus 1 plus 1. What is t of n minus 1? It is n minus 2 plus 1. So we will substitute this here. So we will get t of n minus 1 is t of n minus 2 plus 1, plus this one comes here. Solve it, you will get t of n minus 2 plus 2. Again now t of n minus 2 is t of n minus 3 plus 1. Substitute it, you get t of n minus 3 plus 1 plus 2. So 3. This keeps on going. So some k I will take. So t of n minus k plus k I will get. No matter which number it is, always I will keep on getting t of n minus k plus k for this particular type of problem. So we know that the base case for this is for n equal to 0. So I have to get t of 0, which will give me 1. How can you get t of 0? This is when your k becomes n. So whenever my k becomes n, I will get t of n minus n, which is 0. That is my base case. So the recursion stops there. So I will substitute. So I'll get t of n minus n, that is, I will put k equal to n, plus k is again n. So I get t of 0 plus n. What is t of 0? 1. So t of n equal to 1 plus n. So again, I want to write it in the multiplicative form of a function. So I will take n out. It will become 1 by n plus 1. So this is again of the form f of n equal to g of n into some constant c. So again, I will tell t of n is big O of n. So this particular problem can be told as it has linear complexity. So this is how you solve a recursive problem using substitution method. We keep on substituting it until we find out what is the base case and when to stop it. And once we stop it, we try to notate using some asymptotic notation. Thank you.